Welcome everyone to the week 2 tutorial session of Galois theory course MA70. Today we'll discuss some questions related to week 2 lectures. Let's begin. Okay. Okay. So these are some questions from the assignment only, which are non-star, non-blue. So you don't have to submit those questions. So I can discuss those questions. That's why. Okay. So let's try this question. Let K be a field. Okay, K is given to be a field and F is A0. F is a one variable polynomial in the field K. So that is Kx. Okay, I'll keep consistent notation. So K is a small. So this is a polynomial in Kx, and define this new term a0 plus new polynomial a4 x square up to and so on, and like last term will be dependent on n. So if n is odd, then it will be. So basically these are even places in terms of ai where I is even. So this is corresponding to that, and the last term will depend on what n is. Like if n is odd, then it won't appear. So for example, if n is odd, then it will be a n minus 1 x raised to power n minus 1. Okay. And if n is even, then this polynomial, then the last term will be a n x raised to power n. Okay. So yeah. And also f1 denotes a1 a3 x, like odd places thing. So a raised to power 3 square up to and so on. Now again, if n is odd, then it will be a n x raised to power n if n is odd, else it will be this. Oh sorry, right, I have to so degree of x is something different. So we are having one. So can you tell me what will be the degree here? So it's like corresponding to a2 what we are getting, x raised to power 1, corresponding to a4 x square. So it's like you can say half of the like whatever it is n minus 1. So you'll get n minus 1 by 2, because n minus 1 is even, then by 2 makes sense. Is that okay? Is that clear?
Okay.
Yeah. And what about this x raised to power, like for n is even, what should I write? Again, n by 2 will work, right? So n is even, then n by. So for f0, all the powers of xi is like we have a coefficient, and whatever indices for corresponding to that coefficient, we will just take it and take its half. Okay. In f1, what will happen? You have an, and the power of x will be something like n is odd. So that means so what is happening? You have 3, you have this one, you have 5, you have 2. So it's like you are taking alternate ones and you are keeping x's to be the same. So you are doing half of the power. But which power? So you have 3, then you are subtracting by 1, you are getting this 3 minus 1 by 2 as the power of x. Similarly, for this one, you have 5 minus 1 by 2. So it's like you can write, so here you had n, so n minus 1 by 2, which makes sense because n is odd. And here also you have n minus 1, you subtract by 1 and you divide by 2. Okay, so if n is even. So this is something you have given to be some other polynomials corresponding to f. Now, what has been asked? Prove that to show x square by a divides f in kx, small kx, if and only if f0 of a and f1 of a both are 0. Like a is a root of both of the polynomials. And yeah, right. In kx, that means a belongs to k. Okay, we don't need to write because it is like divides in kx, that means a is in k. Okay, so we need to show that. Do you get some intuition regarding how this is turning up, or like can anyone tell me? So how should I realize these f0 and f1 in terms of f? Can anyone give an idea?
Ma'am, if it divides that one, that polynomial has some odd coefficients and even coefficients. So we can split that polynomial into two polynomials, sum of two polynomials.
Okay.
Because
Which one? F itself, or you have divided already?
no, ma'am. What I'm saying is, suppose x square minus a into g equal to f.
Yeah, right. X square minus a into g is equal to f. Right. Yeah.
Okay. Then we can split g into two polynomials.
Right.
Such that one polynomial has all odd coefficient, odd degree monomial degree, and so one polynomial has even degree.
In g itself, you are saying?
G itself, yeah.
Oh, okay. Okay, we can try, but I don't think it will turn up something good in the sense of f0 and f1. Or let's try to divide and see what g is coming out to be, because we have in hand.
What I'm saying is, those two polynomials G1 and G2,
Right. G1 and
G0 and G1.
right.
G0, G1.
Right.
X square minus A into G0. That would be one polynomial plus x square minus A into G1.
Okay.
In this one, in first one, all are odd coefficients.
Why exactly? Because firstly you took g and then you divided in terms of f0 and f1 as we defined.
No, forget about f0 and f1, ma'am.
Okay.
So,
but what is g0 and g1?
Suppose g equal to b0 plus b1 plus b2, something like that.
Similar to the earlier definition, these definitions, right?
Earlier definition.
Okay.
So split this into two polynomials, like b0 plus b3 into x cubed,
Okay.
like that.
Okay.
And second polynomial is b1x plus like that.
Okay.
b2x square, ma'am. b2x square.
b2x square.
Like that. All
it's
even
not
powers.
square. It will be just x. Right?
Yes, ma'am. Yes, ma'am. Plus, this is one polynomial. Another polynomial is x square minus a into b1x. B1x.
Yeah, yeah. Okay. This expression, right?
No, ma'am. One thing. Here b1x, ma'am. Not b1. Just.
Oh, no. It's b1 only.
Because
this is the polynomial a1 a3x. There is no x here with a1.
No, ma'am. Means in G, x is also possible, right? b1x, ma'am. Here b2x square, like that. We are splitting into two polynomials.
Okay. You are saying you split into polynomials. Okay, but then it will be x raised to power 4.
That's what I'm saying. That is what I'm saying.
Okay. You split in
Okay,
this.
then this,
So that x square minus a divides f in kx.
Okay. Maybe you try this out because at least I don't
Sure, ma'am,
have
sure,
this
sure.
one.
Okay, you can carry on. Yeah, no problem.
Yeah, you try it out because I think the term will appear in the remainder, so I'm not very sure if G will play any role, so that's why I'm not sure, and maybe this could give something, of course, because at least it is dividing. So what I'm saying, let's try this. So how these terms are appearing, that's what I was asking. So like if you take x square minus a, because because at least in my explanation, remainder will have this f1
So we
f0
can
term.
write f as a like f naught of x square plus x times f1
F
of x
not,
square.
no, because
No,
what.
means we are replacing x by x
Ah,
square.
okay.
Means
Okay.
f naught is in x, so x is replaced by x square.
So
Similarly,
you can say this, right? X
plus
into f1.
yes.
Yeah, maybe x square. Oh,
Now by dividing by x square minus a, that means x square is same as a.
right.
So
So,
so a is a zero of the is zero of polynomial f.
right.
That implies that x that
So,
one way is clear now.
yeah, right. So, yeah, exactly. This is one way, of course. So, you have f of x. You write f0 of x square plus x into f1 of x square. How you are writing? Because you just take a0 plus a2x, you have this term. Other is a1 plus a3x plus a5x square up to and so on, and you have this f0x, and you will get from this f0x square, it will be a0 plus a2x square. So powers will be managed in that sense, a4 x raised to power 4 up to and so on, and here x1 of x square will get this, and you will get 4, and then you multiply by x. So is that clear for everyone? So what he's saying, you take f0 x square and you will get this polynomial, okay, and then you take f1 of x and you replace x by x square, and you get this polynomial a1 plus a3x square plus a5x raised to power 4 up to and so on. Now we need to manage degree. We want a1x, so we just multiply by x in f1 part, and we will get this relation. So is that clear for everyone? Sorry, I don't know the names, but
So,
yeah. Okay. So f1 of x square. So you have this, right? Now, as he said, if you put x square is equal to a, x square is equal to a, then f of a, sorry, not f of a. So you will be looking at, okay, I should say x square minus a divides fx. So if you replace x square by a, how will you proceed? Sorry. Uh, how will you proceed? So we need to prove x square minus a divide fx if and only if f0 of a f1 of a is equal to 0. So if you have f0 of a is equal to 0 and f1 of a is equal to 0, then f of x is equal to 0. So that means x square minus a divides that. In the sense, at least you can write, you can do
Means when x
yeah.
square,
So you write
the
like
forward
this.
implication that x square a is a root. It says like x square minus a divides f. That means x square is a, because x square minus a is a factor. So
Just a
x square
second.
means
Okay.
square root of a is a root of that polynomial. So when we replace it, in this expression f naught plus x f1, that
So
is all of 0. Now the one f naught part is of even degrees, and the f1 x f1 is of odd degrees. So if it is equal to 0, then both of them has to be 0 separately.
yeah.
So all of the coefficient
Right. So
should be 0.
basically, what you are saying, and even that is that is what I was going to prove. That claim is fx is equal to x square minus a gx plus f1ax plus f0a. So what I'm saying, in division algorithm, when you have to divide x square minus a, when you divide x square minus a to fx, you will get quotient and remainder to be this exactly. Like quotient, I don't care, because I just so I don't need that, because I just want, if it divides, it divides. So and so what we are saying, so this is the claim, and yeah, right. So this is the claim, and which implies, and if this is true, if claim is true, then what will happen? f1 of a x plus f0 of a is equal to 0, because x square minus a divides fx if and only if, because this is a unique representation. So firstly, k is a field, so you can apply division algorithm first thing, and division algorithm says you have gx and rx. So division algorithm, when you divide fx by gx, oh, I should not write g, or maybe when you divide fx by hx, then you will get some quotient and remainder which are unique, okay, and degree of rx will be strictly less than degree of hx, or rx is equal to 0. So this is division algorithm, and you are in a field, k is a field, so kx can have this division algorithm, right? Is that clear? So what I'm saying, if you prove this claim, we can get x square minus a divides fx if and only if this remainder, because now you can say this is a remainder, because this is I'm not saying this is true, I'm not saying claim is proved. If I prove this claim, then this remainder part is equal to 0, okay, if and only if x square minus a divides fx, and this is and also this is fine, this is a remainder, because degree of this remainder uh, is equal to 1, or whatever it could be 0. If f1a and f0a equals are 0, then remainder is 0. If f0a is 0, then it has degree 1. If f1 of a is equal to 0, then it has degree 0, or like all the possibilities, but it has degree, if it has, if r is non-zero, then it has degree less than 2, okay. So this is an expression of division algorithm, okay, and this is unique, so we don't need to care if there is any other possibility to say that this is 0 or something, okay. So if claim is true, then x square minus a divides fx if and only if f1 of a x plus f0 of a is equal to 0, and which implies, since x is a variable, so f1 of a as a polynomial, all the coefficients has to be 0. So this has to be 0. Is that okay? So I'm saying, if I prove this claim, then we are done. And what he was saying exactly, I think that's because if this is exactly we are getting as an argument also, right? Is that okay? This claim is clear. I'll prove this claim, of course.
Notation that you used f1 or f0 that already been used, so can we use it some other
No,
notation?
I'm saying these are the exact like these are the same FIs. So I'm saying, if you define this okay, so claim is f of x is equal to x square minus a gx plus f1 of x plus f0 of x. Sorry, not x. A and f0 of a, where gx, I don't know any information about gx, so I'll just say this belongs to, sorry, not fq, k x1 to, this is one variable, right? So kx, where gx is something which belongs to k. Gx is some polynomial in kx, and f1 of a and f0 of a are exactly coming from the representation of f1a and f0 of a. I'm not saying these are something different. This is exactly I'm using, because these are some polynomials. You put a here, at this place you put a square, then so f0 of a is equal to a0 plus a2 a plus a4 a square up to and so on. And here f1 of a is equal to a1 plus a3 a plus a5 a square up to and so on. Is that clear? These notations I am using. Notation as in the exact value. So this is exactly a way to think that. So fx is
okay, the whole term is f of a.
Yeah. Sorry.
Okay, f of a the remainder part is f of a.
Remainder part is f
the
of
whole,
no, not f of a. When you put x square is equal to a, then this will become you don't know what, so root a or something, like I cannot write that. So x square.
okay, so like remainder part is f of root of it, kind of.
Yeah, kind of. Yeah, I cannot say
Okay.
about that. Yeah.
Okay, that you had split it.
Yeah,
F1
because
is
we
okay.
cannot say root a and these
We are
things.
replacing x square by a, means kind.
Yeah, right. So you are saying x square minus a. So x square minus a divides fx if and only if this part is 0. This makes sense, because if it divides, then remainder.
Carry on, please carry. Yeah.
Is that okay? Okay, great. Okay, so yeah, so proof of claim. So even you divide it, you can realize that this is turning up easily, like x square minus a. If you divide, you will get, like, if I write a n x raised to power n, a n minus 1 x raised to power n minus 1 up to and so on, a 0. So when I divide this, at least I'll do one step, at least two. So you will multiply by x raised to power n minus 1. So I'm just doing division normal sense. You will get a n x raised to power n minus a n x raised to power n minus 2, right? So this is this. You'll get this x raised to power n minus 1 is as it is, and you have, so a n x raised to power n minus 2 is coming from here, and then there is a term like this, right? This is a polynomial, so I can write. And you will get a n plus a n minus 2 x raised to power n minus 2, and so on, the other terms of the polynomial, or a n minus 3 x raised to power n minus 3 plus up to and so on. And then again, next step, what will you get? You will multiply by a n minus 1 x raised to power n minus 3. So that's what I was saying. I cannot realize that in the quotient, because you are, like, there might be a way, but I'm not sure. But so you will get a n minus 1 x raised to power n minus 1 plus, not plus, so minus a n minus 1 x raised to power n minus 3. So a n plus a n minus 2, and here you will get a n minus 1 plus an minus 3. So these terms are same, like the powers of x is same. So you'll get this and so on. Okay, so if I say, for example, n is equal to 3, then what will you get? You have to stop here only, because n is equal to 3, then this part is just this is just x an plus an minus 2, and here you have an minus 1 plus an minus 3, and so there is no power of x. The power of x is 0 if n is 3. So you will get this. Now this is like your n is 3, so this is 3 and this is 1. Okay, and this is 2, this is 2, and this is 0. So this is exactly your f1a, and this is exactly your f0a. Even you do for n equals to 4, like you go one step more and then you try, you will get same thing. Okay, so this is something you can realize that also. So there is no addition here. Okay, but this is not a way to prove that. So whenever this kind of thing appear, we can apply induction and prove this thing. So let's apply induction to prove this
Ma'am, can I take 1 minute? 1 minute.
Yeah.
Can you write like this? F equal to f naught plus x into f1.
No. As he said, so you can write this.
Yes, ma'am. Yeah, means okay. Yeah, like that.
X square. Yeah.
No.
You have to write x square. Otherwise, it won't be same, because you have a0 here plus a2 x square. You have here this, and from f1 you have a0 plus a2 x. This part is like the power is not same.
I got it, ma'am. Got it.
Yeah. So you have to have this x squared.
Yeah, okay, ma'am. Okay, got it. Where I went wrong. Yeah.
Okay, great. Okay, so let's apply induction. Induction on n.
But that need not necessarily be true, right? Like if I define f naught of x as a naught plus 0 times x plus a2 times x square and so on and so forth. So basically, it need not actually just be f naught of x square, is what I'm trying to say.
Not really. Why? Because so you are defining f0 or f1, only fx.
F0, any one of them, that's fine.
No. So you take fx to be what? A0
plus 0 times x.
Okay. Yeah.
Basically, every odd coefficient is 0.
Okay. Yeah. Then.
And then a2 and so on and so forth. So. Yeah.
So for defining f0 and f1, you are using exactly. We don't care if coefficient is 0. We will write that in the expression. So what I mean to say, if you even have this a0 plus 0 into x plus a2 x square plus a3 is 0, so 0 into x cube plus a4 x raised to power 4. You have something like that. Then if you want to take f0 of x will be what? A0 plus a2x plus a4 x square, right?
My point was not about f of x, it was about f0 of x itself, because you said it has to be strictly f0 of x square and not f0 of x.
Like at least as a polynomial this will be. But for example, here in this example, I will get f1 of x is equal to 0. Then even if I say f1 of x or f1 of x square...
My point was, why can't we write it as f of x as f0 of x plus x times of f1 of x?
Not really, right? At least in general expression we cannot write. Because you will... so, okay, let's see. So you have fx, you have fx, you have f0 of x plus x into f1 of x. From here you are having a2x plus a4x square, right?
Yeah.
And from here you have expressions like you have coefficients, this a2x square plus a3x cube, right? How will you compare this? Like, this is a2x, and so the coefficient appearing here only. From the other part you will only have a3 and a4 kind of expressions, like a3 odd ones. So how will
Okay,
you
okay,
say
I
that?
get the point. No,
Yeah,
so
at
I was
least
just
in
saying,
general. So you might be picking particular value so that this is 0, and but we are talking about the general
okay,
ones,
fine.
like, yeah, because fx could be anything. We have to prove for every case. Okay, so let's see. Yeah. Okay. So let's try induction on n. And so for induction on n, if f is 0, firstly, if f is 0, you have nothing to prove, because x square by a will anyway divide, and f0 of a, f1 of a will be 0, because these are 0 polynomials, right? So we have nothing to prove. And if you take if you, so induction on n means degree, I mean degree of so 0 polynomial, let's discard anyway, okay? Because if I am applying induction on degree, 0 will not be there because degree is not defined. Induction on n, which is degree of f, okay? F could be anything now, because when you apply induction, polynomial could be taken anything. Okay, so when you take, so if you take n is equal to 1, or firstly 0, if you have the constant polynomial which is non-zero, fx is a constant polynomial, just a0, okay, then what will happen? You will x square by a will not divide this, right? And even what will be f0 of this is non-zero, okay, because I'm saying the f is a non-zero polynomial. Then what will be f0 of x? It will be f0 is a0, just the even part, okay? And that is non-zero. So this is non-zero and this is not dividing if and only if condition so this is like tautologically true, okay? Is that case clear? N equals to 0. Okay, let's see n equals to 1. Okay, I'll go at least till n equals to 2 to explain it. So n is equal to 1 means a0 plus a1x, and a1 is non-zero, right? Degree is 1. Then x square minus a will not divide fx, because this is a non-zero polynomial, because fx is a non-zero polynomial and degree is 1, so this cannot divide, right? And from the other side, what will happen? F0 of so f0 of x will be what? A0, and f1 of x will be what? A1, right? Is that clear? I have no information about a0, because a0 could be 0, because we just know that degree is 1, so a1 will be non-zero. So I have information about this, and this is not dividing and this is not equal to 0, so this is okay again for n equals to 1 case, because what we need to prove or okay, so I can even say in terms of claim also. So uh, so claim and these things are same, because I'm saying gx is anyway 0, because degree of x square minus a is 2, so quotient part is anyway 0, so we are just talking about remainder. So let's see this n equals to 2 case. So fx is equal to a0 plus a1x plus a2x square, okay? Then f0 of x will be what? A0 plus a2x, and f1 of x will be what? A1, right? Okay. Now how will you write fx? Can you give some expression for gx plus? Now what I want, I at least want so I'm saying, okay, let's remove. So I want to write fx in terms of x square minus a gx plus rx, where rx is exactly this 1 x plus f1 of f0 of a. So I'm still keeping it blank. You can tell me what this should be. F1 of a is what? F1 of this implies F1 of a is equal to a1. So you have a1x. What is this? This will imply F0 of a will be a0 plus a2a. So this is a0 plus a2a. So can you tell me what should I take here? Gx could be anything. Gx is this quotient. So what should I take this so that it will become equal to fx?
A2.
A2, right? So yeah, we just take it to be a2. Then what will happen? You will get a2 x square minus a2 plus a1x plus a0 plus a2a, and this will get cancelled, and you will get just a2x square plus a1x plus a0, which is your fx only. So and this is a unique expression. As I said, if we can get one expression, then that's okay, then we are done. So for the case of, so what we have proved, fx can be written as x square minus a into some gx. Here gx is this, plus f1 of a into x plus f0 of a, and we did that for the case of n equals to 2. Okay, so we apply so our hypothesis is induction hypothesis, or so we assume okay, so claim is true, assume that the claim is true for all m less than n. Okay, let's assume n is some natural number. We are saying for it is true for every m which is less than n. Okay, so let's see. Okay, so you want to write fx to be in terms of the remaining part. What we can do now, we know the result for degree less than n. So we already have fx which has degree n. So how will I go to one step down? One step down means how can I get hold of some polynomial which has degree n minus 1 or less? What can I do for just one step at least? So what I'm saying, can we do something on fx so that I can get hold of one step? So okay, what I'm saying, you divide by x square minus a. Okay, so we did that here. So you divide by x square minus a, then when you divide x square minus a to this polynomial by x square minus a of fx, then you get this expression. Okay, and so let me write this one step only. So I'm saying you divide by x square minus a, when you divide an x raised to power n plus an minus 1 x raised to power n minus 1, then so you multiply by an x raised to power n minus 2, you will get this, plus minus a into an x raised to power n minus 2 plus minus an minus 1 x raised to power n minus 1 plus an plus an minus 2, because you already have this an minus 2 x raised to power n minus 2 term, right? You have this polynomial full x raised to power n minus 2, and you have other terms x raised to power n minus 3. These are from the polynomial itself, no change in the remaining terms. So I'm saying you just take this. So you have fx, you have written it down as x square minus a, because you can apply a quotient, at least you can write here fx is equal to x square minus a, and so you have an x raised to power n minus 2, this part, plus an minus 1 x raised to power n minus 1 plus an plus an minus 2 x raised to power n minus 2 plus an minus 3 x raised to power n minus 3 up to and so on a0. So what I did, I just I divided x square minus, I divided fx by x square minus a, just one step. I'm not saying that I'm writing in terms of something degrees less than or whatever, but we can do this step at least once, okay? And we have this quotient remainder thing. Is that clear? So this expression is clear. That is going to be our major thing. Like, is that clear? This step?
Sorry for interrupting, man. I think give me 2 seconds. I mean, actually, we need not do all these things. But simply, f of x. Suppose x square minus a divides f of x. F of x equal to, as you have said, f naught x square plus x into f1 x square equal to x square minus a into some g, because x square minus a divides f of x.
So you are saying this, no? But how will you come back from the other side? So
Ma'am,
yeah.
because x square minus a divides f of x. If that is assumption.
Right.
So x square minus a, f of x equal to x square minus a into gx.
Okay. Then
Equal to x square minus a into
yeah.
g1x. Sorry, g0x. G
But I'm
x, please.
saying, so I got your point. You will write gx in terms of g1x or maybe g2x. That's okay. But we can do it combinedly. I'm saying you just prove one expression and then we are done from both sides, like if and only if condition.
No, ma'am. No. You are confusing because x square minus a equal to please write down one line. That is sufficient. It is nothing. It is very simple problem. X square minus a into a bracket open.
Yeah. It's lagging. So.
G naught means G naught means a coefficient. G naught plus G2x square, because these are coefficient. G2x square. So dot plus.
Why the?
Please, that is a polynomial. I am splitting G up.
Yeah, I got your point.
Into x square minus a. Into x square minus a. G1 x into x square minus a.
Yeah, I have split that.
Yeah, you have split, right? Equal to the whole equal to f naught x square plus x into
Why? Okay.
x into f1 x square.
Okay.
Now, see, compare these two things. The first split is all even powers. X square minus a into
No.
G
That's okay. I got your point. But these are polynomials. You cannot say that this has to be equal to this or something. Because
no, polynomial coefficients are equal. The polynomials would be equal, right?
right. Yeah.
Means the first split is equal to f naught x square. That's it.
Why the other part cannot be the one?
Second part also x into x square minus a into g1 plus g3 x square. That polynomial equal to x into f1 x square.
But I'm saying these are polynomials. So you are saying in terms of values. You are comparing two polynomials.
Values. Just
Okay,
I am comparing these two polynomials.
Okay,
Yes.
maybe this could be an option, but
It is over. X square minus a into that first polynomial. We split it into two polynomials, right? Gx.
but why these has to be equal compared to this? Like why these has to be the exact
Because
value?
f of x equal to x square minus a into gx.
Yeah. So what?
F of x equal to f naught x square plus x into f1 x square.
Right.
So it means both polynomials are equal.
Okay, this needs some rigorous argument because these
No,
are...
ma'am, no. You are confused. You are just confused.
Okay. Maybe I'm confused. Let me finish my part. Maybe we can discuss
No,
after the
ma'am, it is
session.
over. There is nothing is there. It is over.
Okay.
Means equal to x square minus a into first polynomial plus x square minus a into x into second polynomial equal to this one. So it is nothing but.
Yeah.
So it means f naught x okay, ma'am. One line f naught x square equal to.
Okay, we can continue this part.
No,
That's
ma'am,
what...
no, it is over. It is nothing is there. It is over.
Okay. So this is let's say
F naught
alternate.
x square equal to. Please write.
Alternate solution. Okay.
No, it is over, ma'am. Nothing is there. It is
So
over.
I'm saying, this is alternate solution. Let me complete that solution first.
No,
Why not?
it is nothing is there. That is beating about.
Okay, that's okay. As I said,
Can I talk to something? Vijay? Can I talk to Vijay? Hi, Vijay.
okay, 1 second. I got your point. That's okay. So this is one solution. Let me say that. 1 second.
Can I interrupt?
Yeah.
Yes. Can I talk to you? Who is this? Who is talking?
Yeah, the thing is, you're not. I understood what you're telling, but
I will get us. F naught x square equal to x square minus a into g naught plus g2 x square plus that's it.
No. The thing is, she's asking why is that? Why are you equating those two things?
Because I am equating powers, odd powers, even powers. I am dividing.
Yeah,
F naught
yes.
x square has all
Yeah, it could be possible that some power is here also, some power is here. You can split the values also. You cannot just say that these are equal. Maybe this could be a solution, but you have to write a rigorous argument for that, and that is possible. I'm not saying... Okay, we can continue later because this is recording, so I have to finish in 2 hours.
Yeah, we understood.
Yeah, we can continue later. It's fine. I can discuss
We
after
understood
the...
your argument.
Okay, so let's complete
That
this.
is, we understood your argument. Yes.
Sorry. Yeah, so what we were doing, fx is equal to x square minus a, and you have a and x raised to power n minus 2. I'm saying you take this polynomial. This polynomial is itself what? This polynomial has degree n minus 1 or less. We don't know because a n minus 1 could be 0, but at least it will have degree less than or equal to n minus 1. Okay. Now, when you have this case, you can use induction hypothesis to write this expression. So let me say that this is f dash of x. So f dash of x is equal to a n minus 1 x raised to power n minus 1 plus a n minus 1 plus a n minus 2 x raised to power n minus 2 plus a n minus 3 x raised to power n minus 3, and the other things are same. Okay, so you take now you calculate this f0 of a, not just a, f0 of x. What will you get? You have a0 plus a2x, and there could be other. Now what will happen? Let's now I have to assume what is n. So if n is even, then what will happen? If n is even, then this term will appear. So you will get a n minus 1 plus a n minus 2. I'm assuming n even from now for this part. So a n minus 1 plus a n minus 2, and you will have x raised to power n minus 2 by 2, right? And f1 of x will be what? So I'm doing for dash this polynomial, this new polynomial. Dash is, don't assume it to be the differentiation, formal differentiation. We are just talking about new polynomial. And now here you will get a1 plus a3x plus up to and so on, and you will get here you will get a n minus 3 plus a n minus there's some powers. So x raised to power n is even, so you will have n minus 4 by so for this you just subtract by 1, So we did that in the beginning. Plus a n minus 1 x raised to power n minus 1 minus 1 by 2. Okay, so you got these two expressions, and note that you will so when you take a, you will get a0 plus a2a up to and so on, an minus 1 plus an minus 2. So there is a also, a raised to power n minus 2 by 2. And f1 dash of a will be a1 plus a3a, an minus 3, a raised to power n minus 4 by 2, so isn't this, plus an minus 1 x raised to power n minus 2 by 2. Okay, note that these are equal to f0 of a, and this is equal to f1 of a, because what you need, you have a0, a2, and in the end what you have, an minus 2 into a raised to power n minus 2 by 2, and you have this part, a into you have a into an minus 1. So when you multiply, you have this part also, which was something missing in the sense that when you go degree down, so it is captured here. So when you multiply by this an minus 2 by 2, you will get this exact power. So these are actually equal to f0 and f1 of a. Now from the expression of from the induction hypothesis, this is exactly fx is equal to, you have x square minus a, and this is equal to an x raised to power n minus 2, plus from the induction hypothesis for f dash, I am using induction hypothesis, so this is f dash, so that will be equal to x square minus a some g dash x, some polynomial, and the from the claim, the induction from the induction hypothesis, this will be equal to this x plus f0 dash a. And so what you can do, you can just combine this. So this is your new gx, so an x raised to power n minus 2 g dash x, plus this is equal to, as we have observed, that this is equal to f1 of a and f0 of a, and this is your new gx. So you have written fx in terms of this, and we are done. So yeah, this is one explanation at least. There could be plenty, and that argument could be okay, but maybe, so you can just write it down properly. That is okay, I can see that, but yeah, I also need argument to write. Okay, so is that question clear now? And yeah, let's move to the next question then. Okay, let A be an infinite integral domain. And f, g and h belongs to A, x1 to xn, and h is not equal to 0. So these are some polynomials such that f of a is equal to g of a for all a belongs to an. Okay, so a belongs to an and h of a is non-zero, like all those points. So what has been asked, what is given? So there are three polynomials f, g and h in the polynomial ring ax1 to xn, where h is not equal to 0, so this is not a zero polynomial, and these f and g are such that f of a is equal to g of a for all a belongs to an, wherever h is non-zero, h of a is not equal to 0. So all those points where h is not equal to 0, then you have to prove that f is equal to g. So this is a very strong statement. So, yeah. Okay, So we can recall this identity theorem for polynomials. What does this say? So so basically what you are saying, two polynomials are same at some big set, so that has to become 0. So for example, when you take just so let's see this part only. So let A be an integral domain. So from the identity theorem, A be an integral domain and f and g belongs to ax1 to xn, be two polynomials such that their partial degrees means you have some polynomial, let's say f is equal to x1 raised to power 5, this you have something like this, then degree of x1 in f is equal to 6 and degree of x2 of f is equal to 1. So the highest degree of xi which appear in f. Okay, so this is these are partial degrees. Total degree of f will be the exact degree. So for example, I might have something like this, then so the total degree will be just 6 because the total power you can have. So if I have more than that, let's say I have this 3, then the total degree will be 7 of f. Total degree means sum of the powers you are having in the terms, maximum of that. Okay, so with respect to the indeterminate xi is Ri. So you have degree of xi, yeah, such that this is less than or equal to. So I'm just explaining the statement of identity theorem. If f and g are such that f and g belongs to ax1 to xn and degree of xi and degree of xi of g is less than less than ri, less than or equal to ri for all I, and there are some sets ni such that cardinality of that is greater than ri for all I, and such that f of so a1 to an, you can say, is same as g of a1 to an, such that these are equal for all. So I'm writing this to be a bar means the tuple. This belongs to n1 cross n. So you have n variables. If you have this thing, then f has to be equal to g. So you are saying you take the degree of f and g, and the point is these are infinite integral domains. We are not saying this is true in finite fields or something. So you take infinite integral domain, and if degree of f and degree of g with respect to xi is less than or equal to I, and you take some bigger set corresponding to each xi, and f is 0 on those points where ai belong to this set, then f has to be equal to g. So it's just you take, if it is 0 at big enough set, then the polynomials has to be 0. So yeah, you can think of f minus g also. So that's what I'm thinking. So I'm saying if f and g are equal at some big enough set, then f and g as a polynomial has to be equal. So that's the identity theorem. Yeah. Yes, Vijay.
Ma'am, can we take a like in particular some example, like
Okay.
take n equal to 1 and explain the theorem?
Okay. So theorem says if you take n equals to 1, now you can actually say, so A is an infinite field, infinite integral domain. So n equals to 1 we have done with Vita theorem. So if A is an infinite integral domain, and you know that you take a polynomial, so you take so I'm just taking f minus g's to be so you can explain this this theorem to be like if f minus g at a1 to an is equal to 0, then f minus g has to be equal to 0. So I can think of just a polynomial. You replace f minus g by h. So you are saying if h is 0 at begin of set, then h as a polynomial itself is 0. So for example, you take a to be a infinite integral domain and n equals to 1, and you take fx to be something, let's say right now I'm taking some general one. Then okay, so how shall I say? So
So let's
how
take
many
f is
roots?
x square and g is x cube.
Yeah,
Then
right.
the identity
So
theorem, what it says.
okay, so x square and x cube, you cannot fix those things. You have to find these AIs also. So let me explain in just this part. So you take fx is equal to x square, and you are saying it is 0. So it is 0 at 0, right? And this is an integral domain, so that
Yes.
is the only possibility, right? This is an integral domain, so that is the only possibility. So what we are saying, so here theorem is not applied, because degree of f is equal to 2, and number of zeros as in number of zeros is equal to just 0. So the cardinality, this n1, the cardinality of n1, so this is n1, and cardinality of n1 is equal to 1, but the degree of f is 2. Degree of f with respect to x is 2. So you cannot apply the theorem. So as I said, theorem says you just think of one polynomial, don't think two polynomials. You can think f minus g, that's what I'm saying. You think of f minus g, and you replace it by some, you can call it a new polynomial, let's say h. So h is 0 so this is your a, at a belongs to n, okay, and cardinality of n is greater than degree of f with respect to x, that is 2. If you have this case, the cardinality of n is bigger than that, then only you can say h is equal to 0. So here the case is not applicable.
Can you give an example of such function?
Okay. So basically that polynomial is itself 0, so I cannot give an example. That's what I'm saying.
Fair, okay.
Yeah, so you have to have this 0 polynomial. That's what I'm saying.
Maybe in two variables.
Not even two variables, because the polynomial itself has to be 0. From the identity theorem, when you take h to be something like that, then h has to be the 0 polynomial. I can only say that if h is non-zero, then
We just want to understand what are these NIs. Tell NIs, how to choose and like.
So not choose.
1 minute, if I could just, so if my understanding is correct, so if I have, say, a quadratic equation,
Okay.
and this quadratic equation is getting satisfied at more than 3 points, this means that the polynomial itself has to be an identity polynomial, or like a 0 polynomial, because otherwise it cannot. Fine, I understood.
Yeah, exactly. And you know that with one variable, you know that it has at most d roots. Like I cannot say generalizing that, because so we are in integral domain. So you have at most d roots, at most degree roots. And if you say it is more than that, then the polynomial has to be the 0 polynomial. That's what the theorem says. Yeah, and this is in multivariable thing. So we have the theorem for one variable, but not for multivariable. So identity theorem gives that multivariable generalization. So you just need to pick ni to be such that it is bigger than the degree of each xi, like appearing in f and g. Okay. So this is the identity. So you have to use this identity theorem. Now this NIs could be anything. Like in this theorem, if you can produce such NIs, then you can prove that this f is equal to g. So in your question, what does this say? If A is an infinite integral domain and f, g, h are something like that, and fa is equal to ga for all a belongs to an whenever ha is not equal to 0. So the point is, this is something which what you have to prove that this set, so all those a such that ha is non-zero, so this set itself is big enough, like you can create some ni from this set, then you are done. Like, so corresponding to each degree, like the degree of xi, you have to produce some this h from this information, you have to produce such ni's such that you can use in identity theorem and prove that f is equal to g. So that's what question asks. Okay, let's try to prove that. So yeah, so this was the part. So if you want to use identity theorem, we have to produce these ni's. So let's see what we can do. Right, so let's so firstly I'll just transfer this question to f minus g and think of just one polynomial. So what I want to say, you take f minus g, okay, I should not use, oh okay, h was a confusing thing. You can, okay, so what I'm saying, you are saying fa is equal to ga for all a belongs to an, and h of a is equal to 0, and h is itself not a zero polynomial. That is one thing which you know. So a belongs to an and ha is equal to non-zero, not 0. So this is something, a set. Then you have to prove that f is equal to g. So that is what the question asks. So I'm just changing this system to be like this, and f minus g is equal to 0. So f minus g of a is equal to 0 for all a belongs to an, and ha is not equal to 0. Okay, now I can, so because of this I can say that without loss of generality, I just assume f minus g is to be f. Okay, or if you want to introduce some new variable, you just say capital F. Okay, so f minus g is equal to capital F, so f minus g x is equal to capital Fx. So we want to prove that if f is equal to 0 for all a belongs to an and ha is non-zero, all those a such that this property holds, then so these are combined, like all those a such that ha is non-zero, then f of a is then the polynomial itself is 0, f is equal to 0. Okay, so this you need to prove. So okay, so let's define this set D.
I think this condition that you have written, that f of a is non-zero for all a is in an. So like a.
Sorry. F of a is non-zero.
0. Yeah.
H of a.
It's considering only like capital F is f minus g, right?
Yeah.
So f and g agree on those points of an where h is non-zero. Like right. It's like a polynomial, the zero set of h that in complement it right. agrees on the complement.
Right.
So if any two polynomials which agrees on the complement of zero set of h, then they has to be equal.
Right,
that is what I think it's saying.
Yeah. That's exactly the question is. Yeah.
So here a is in an minus 0 of h. That is what we know.
Right.
When you write,
I can define.
And h of a is non-zero.
Right. So what we can write, v of h. Okay, in the field we have a field, so we have a at least, an maybe. So this is all those points a belongs to an such that h of a is equal to 0. So I just define, so basically if you think in terms of geometry, you can say that this is an open set, the other one. So you have d of an, this is equal to all those a such that h is non-zero. So I just denote it by d. Okay, and so this is actually what, an minus variety, so yeah, zero set of this. Okay, So minus this.
Ma'am, just a side query, means
Yeah.
like remark. Is it true? Is it the same thing it's saying that open sets are dense? Means like any two polynomials which agree
Yeah.
on the complement of H. Yes, is that the same
Yeah,
thing?
it's like
Because
it agrees on a dense set, then it has to be equal like this. Yeah. Yeah.
so open sets are dense. That is what. Okay.
Yeah, open sets are dense.
Yeah,
Yeah,
that is the
open
proof. Okay.
sets are dense in the terms of Zariski topology, if you know, because you're not saying in metric space.
Yes,
that
yes, yes,
yeah,
yes.
yeah. So
Yes,
yeah,
just asking.
Thank
Thank
sure.
you.
Okay, so yeah, this is let's we don't need to understand geometry for this, but yeah, so the notation are coming from there, but that's okay. So you define this D to be this set where H is non-zero. Okay, all those points where H is non-zero. So what we are saying, if we can produce these n1 to so let me write. So let's degree of xi of f is equal to ri. Now we use the same notation. So degree of f, this new f, degree of so less than or equal to I. Let then we have to produce some ni. So task, we have to produce this n1 cross so we have to produce ni such that ni's are subset of A, such that cardinality of ni, the elements in ni, are greater than ri. So we have to find such ni's where where h of so such that and h of a1 to an is equal to 0 for all ai belongs to ni, or no, not like that, for all a1 to an belongs to n1 cross n2 cross up to and so on n. So that's what we are saying. So that is not equal to 0. So we are saying h is not equal to 0. Just forget about f now. From the identity theorem, if we can produce some ni such that this condition holds, and these are so f is 0 at those points, and now f capital F is 0 on those points, means h is non-zero on those points. That's what the condition says, right? So condition says this f is 0 on those points where h is non-zero, right? So if we can prove h is non-zero at big enough set, then we are done. So we will just prove that these ni's are coming from this h, and h of a1 to an is not equal to 0 for all a1 to an belongs to n1 cross n2 cross up to and so on nn. That means all the ai's are in ni. Okay, so this we need to prove, to show. Okay, so we again use induction. Okay, so for one we have already proved. So proof, use induction on n, again on this variable n. Okay, so for n is equal to 1, we already know by the theorem. Okay, we already know that f is 0 at this much, so from the degree we know that already. So what I mean to say, f is equal to 0 for degree of f is less than, whenever degree of f is less than so induction on n means okay, so this n and degree are not the same. So let's say degree of f is equal to, I just denoted by m. Okay, this n is different. This n is coming from x1 to xn, from the variables, from variables. So if I take just one variable, then we know that fx is equal to 0 for f, for only m many points, for at most m many points, okay, of A. But A is infinite, so from the so we know that this polynomial has to be 0, because we know that it can only vanish on m many points. But we know that it is varying on, so degree of x f is equal to m, and we know that n1 is greater than, so yeah, what I want to say, so I should write what we are assuming.
Greater than m.
Yeah. I should write in terms of h. That's what I was thinking. Sorry, one second. So, why I'm writing f? I should not write f, because I have changed the question in terms
H,
of
degree of h is m.
Yeah, degree of h. Yeah, degree of h is equal to m. Okay. Yeah, degree of h is equal to m, and h of a is not equal to, so h of a is not equal to 0 uh, for so what I'm saying, a is infinite. A is an infinite set. It can be 0 only on m points. Okay, so that's we can write this. So v of h is less than, cardinality of this set is less than or equal to m. So this implies d of h. So d of h means all those points in at which it is non-zero. So n is just 1. This is equal. This will be great. So this will be infinite. This cardinality is infinite, because A is an infinite set, and you are saying it is 0 only on m point. It can only be 0 only on m points. So at other points it has to be non-zero. So the cardinality of the set where h is 0 is an infinite set. So this is infinite. So what we have proved that there exists some ni. So this implies, so you just take some set. So from this infinite set you just pick some points. So pick n1 which has cardinality equal to m plus 1. Right, you just pick some m plus 1 points, and we are saying h is equal to 0 at those m plus 1. H a is not equal to 0 for all a belongs to ni, and where n1 is a subset of DAH. DAH means where it is non-zero. So we have proved that when n is equal to 1, then we have a big enough set where h is non-zero. I hope this is clear. Yeah. So now assume.
Ma'am, can't we directly use this over there? So if, for example, the number of zeros or the number of points where h of x is not 0, I'm not saying for n equal to 1, I'm saying for anything.
Okay.
Right? If that is finite, then this goes, because h is a polynomial, this is not possible.
No. It is 0 for how many points?
No, if that is 0 for an infinite set of points.
That is possible, right? You just take x1 in ax1 x2. Then it is 0 at all the points of this kind. So you take hx to be this, then you just need to fix x1 to be 0.
Okay.
So this is not true for so the variety, like the 0 set could be big, could be infinite for multivariable thing. So we cannot directly use that. Is that okay?
Yeah, fine.
So that's why we know this fact for n equals to 1, but not, and this is not true even for infinite. Yes, Vijay?
Here we are using the A is an integral domain, infinite integral domain, right?
Right.
So is this statement true that any polynomial of degree n, if any polynomial has zeros more than its degree in any integral domain, then it has to be 0? That is what it's saying, right? Means
Yeah, yeah, yeah.
any
Right,
polynomial
right.
cannot have
In one variable.
more than
in
zeros
one,
than its degree in any integral domain. In field, we know fundamental theorem of algebra, but if I replace it by an integral domain, then in its statement is true, right? It's
yeah,
saying it's
because
general statement.
okay, so you
For n
can
equal to
prove,
1.
yeah, you can prove in the sense that so basically integral domain, so integral domain is important, and you can actually divide by so this fact I'm using. So for division if
No,
you
the identity theorem only for n equal to 1. That's the statement, right? If I take n equal to 1 in identity theorem,
right,
that's what it says.
yeah, exactly, yeah, identity theorem
So it's
work.
a kind of general statement that, to a fundamental theorem of algebra. We just extended the not extended the condition that K is a field. We reduced to an integral domain, but it should be infinite.
Yeah, fundamental theorem of algebra is for complex numbers.
Yeah, complex number. So yes.
Yeah.
So any integral domain, infinite integral domain, that statement is true.
Right, even that's what I'm saying, like okay, yeah, so so like division algorithm, if you take from which you are dividing, if you take it to be the monic polynomial, then you can do that in the normal sense. That's what it is using basically. Okay, yes, Nageshwar, no?
Sorry for interrupting again, ma'am.
No.
1 second. Suppose one page. Suppose h is not equal to 0. Okay. That they have given. So there exists a pair a1, a2, a3, an such that if you substitute that one, that won't be equal to 0.
Right.
So actually, so
H equals to 0, non-zero.
non-zero, right? So
Right.
so it is a polynomial with respect to integral domain k x1 to xn, right? So it is a polynomial with respect to xn with respect to x1 to x1 to xn minus 1.
Right. So
Okay,
exactly,
so,
yeah,
so
induction.
it can't have infinite solutions.
Right.
So with respect to xn, it should be 0 polynomial.
Right.
So then so with respect to that, so it means if you say, so there won't be any
Yeah.
xn term in this one f minus g.
Yeah, you just say capital F, yeah, exactly what I'll do, but maybe small counting thing will appear here. So exactly the induction you are using, you are thinking of this polynomial in terms of just one variable xn. So yeah, okay, let's do that. So assume this state, so this state, when we take induction hypothesis means, so you have this is true for n minus 1 variables or less. Okay, so this statement is true for all n less than n minus 1 or less. Okay, so let's see. So yeah, so exactly as Nageshwar Rao said, since h is not equal to 0 and this is an infinite, so a is infinite, so that means there exists some a1 to an is equal a1 to an in an. So this is not this, so I'm just writing it again. So h is not equal to 0. This implies there exists some a1 to an such that h of a1 to an is equal to 0.
0. So
No, sorry,
if we
non-zero. Okay, let me
non-zero,
complete. Yeah.
not 0.
Yeah.
So if you fix a1 to an minus 1,
Right. Not fix. Okay. Let me do, because I want to use induction. So I will fix an and do it. Let me complete my argument. Okay.
yeah,
So you have this condition, and this is true because a is infinite. This is not true in a finite field. For example, you can have x raised to power q minus x, where q is the cardinality of f. Then this is 0 for all the points, but h itself is non-zero. Okay, so this is not true for finite field or ring, but this is true for infinite. So that's why there will exist some a1 to an such that h of that point is non-zero. Okay, so a is infinite. This implies if. Okay. Okay, so now what you do, you write h of x1 to xn in terms of, you can always do this. You just think of this polynomial. Okay, I'll write here to be 0, and h1 x1 to xn minus 1 xn plus up to and so on h. Okay, degree of h is m. Okay, so hm x1 to xn minus 1 xn raised to power m. So I've just represented it in terms of, like, I'll just collect all the terms which have just xn, and this will be just those polynomials. Okay, so I have just written it down in this form. Now what you do, okay, so you know that h of x1, so you think about this new polynomial x1 to xn minus 1, and you think about, oh sorry, not this, you think about this new polynomial, you define it to be h of x1 to xn minus 1 an. Okay, so here I should have written h is not equal to 0 whenever h is not equal to 0. Okay, so h dash x1 to xn minus 1 is equal to this, and you know that h of a1 to an minus 1, so you define this polynomial. Now we know that h dash of a1 to an minus 1, so h dash is just a polynomial in n minus 1 variables. Okay, I am not using this fact right now. Okay, so you just think about h dash is a polynomial in n minus 1 variables. Then h dash a1 to an minus 1 is not equal to 0 for sure, because we know that when we put a1 to an minus 1, then h is non-zero. So I have chosen, why I have chosen an, so that we will have h dash to be non-zero at one point, because we need that thing. This implies h dash is non-zero, and that we require to use induction hypothesis. So induction hypothesis says that this will happen. So when you have this thing, then if this is true, then h dash is h dash of, I'll write some new terms. This is not equal to 0 for all bi, sorry, not bi, yeah, bi belongs to ni. Now I am producing ni. Okay, because of using induction hypothesis, I know that this will for all I from 1 to n minus 1. So where cardinality of ni is greater than ri. So ri is some fixed quantity. Ri is what? Ri we have fixed. Okay, I'm writing ri to be some this h. Okay, sorry, not capital. So just think about this h. We have totally transferred this in question to h only. So degree of h in like xi degree of h is less than or equal to ri. Okay, corresponding, and these ri's are fixed. That is something we have for h. Okay, corresponding to that, and h dash will have the same degree, because these are just the polynomial in h, polynomial of h with an replaced by some an, xn replaced by an. So the degree of xi will be the same for h dash also. Okay, So you get some cardinality of Ni is greater than Ri. Okay, so you have produced Ni from there. Now what we can do, now think about that. Okay, there is something I need to brush upon. So this is a finite set. Okay, Ni is a finite set. That is important. So
existence of Ni, like we need to show that there exist such Ni's, right?
yeah, I am using induction hypothesis for H dash. So for H dash,
H dash is non-zero and degree of xi is ri same, but we need to show that that Ni.
yeah,
Okay.
from the
Sorry.
induction hypothesis it will exist. That's I should write it maybe properly to show or maybe so. Okay, if H is not equal to 0, then there exists Ni contained in A such that cardinality of Ni is greater than Ri, where Ri is coming from H, and or I can just say from the H only. From H only I'll just fix Ri. There will exist some Ri. There will exist Ni such that this is non-zero on those tuples. So this is the induction hypothesis. So we want to prove that. That means we for n minus 1, I have this fact that if h is non-zero, that's h dash is non-zero, then ni's will exist such that cardinality of ni is greater than ri, and h of a1 to an is non-zero on those points, a1 to this one. Now we have n minus 1 thing. So I have just this part. I don't have the last one. I don't have n for now. That I need to create. From induction hypothesis, this much I have. And we are not sure. So about h, we need to figure out. This is for h dash. So what we have, h dash of, so this is non-zero. So from induction hypothesis, I will get this much information. And Ni is some finite set. Okay, is that clear?
For H, you used identity, the contrapositive statement of identity theorem, right?
No.
Existence
I
of
have
Ni.
not. I have not used identity theorem, and I am not using identity theorem to prove this claim. If I prove this to show part, then I can use identity theorem.
The statement of induction.
Mm-hmm. Yeah.
Statement of inductions, you said that there exists Ni which bigger than Ri such that
so
H
that's not
doesn't vanish.
identity theorem. Identity theorem says if you have such ni's, then the polynomial is 0. Identity theorem assumes that you have ni's. So see this. So you have, suppose that there are subsets ni's, then you can say if it is equal, then on these ni's, then the polynomial is same. Like if you think of 0, if f is 0 at those ai's, then f itself is 0. That is the identity theorem. I am saying if I say h is non-zero,
that means there cannot exist such an n1 n2 nr like nr. See, consider
right.
f minus g, that is my h.
Right. H is non-zero, then
so if h is non-zero, so there cannot exist such ni's.
Yeah, but we are not concluding about h. We are saying about, we want to conclude about f. So what I'm saying, okay. So what does the question say? Question says, if you can prove. So this was the part. So this is the thing we want to prove. If so not even without loss of generality, if fa is equal to 0 for all a at which h does not vanish, then f itself is 0. So what I am trying to prove, if fa is equal to 0 for a big enough set, so this set I don't know, if I can produce some ni's from this set, then from identity theorem I can say that f is equal to 0. So what I'm trying to prove, all those A such that HA is not equal to 0, from that we can find out some Ni's where cardinality of Ni is greater than xi degree of F, then F is itself 0.
So we need to find NIs, right? So
Yeah, we
induction
need to
statement
find,
we need to.
yeah.
Yeah, okay.
And again,
Yeah,
I should write F, yeah, this clears.
Oh, can you explain this induction statement again? Like
Okay,
now how we are
right.
proceeding?
Okay. So yeah, so let me take some page. Okay, so first thing to show from the question itself, fa is equal to 0 if fa is equal to 0 for all a belongs to an such that h of a is equal to not equal to 0, then f is equal to 0, where a is an infinite integral domain. So that we need to prove. To show this, we prove that h of a is not equal to 0. So here I am assuming degree of f xi is maybe equal to ri or less than, doesn't matter. So let's say this is the case, degree of xi f is equal to ri. We prove that ha is not equal to 0 for a belongs to n1 cross nn, where cardinality of ni, we will prove that h is not equal to 0 for all those a belongs to this where cardinality of ni is greater than ri. So we will just prove this, nothing else. If we prove this, so if we prove, so I'll just say this is a star. If we prove star, there is just one hypothesis for, we will prove that if h is not equal to 0, then okay, so this is the if already given. So if we prove star, then by identity theorem f will be 0. So if we combine this star with identity theorem, we can prove that f is equal to 0, because it just required to we have to, because this set itself is the 0 set of f. That's the whole point. Now to prove so to prove star, okay, so to prove star,
Yeah, ma'am.
yeah, so
Now to prove star, can we use identity theorem again? Like
No.
h prime, I'm taking a zero polynomial, a constant polynomial, and that f minus g my new h. Means like in that theorem, what h is, that is my h prime, that is constant polynomial.
But RIs are not coming from h. RIs are coming from f.
No, I'm to prove star, I'm using identity theorem to.
Okay.
So for identity theorem, I need one other h, right?
Okay.
So that this polynomial should be the zero set of this polynomial.
Yeah,
Should be in complement of that polynomial, right?
Zero set of h. Okay, sorry. B.
Zero should be the complement of zero set of
Complement
that
of,
polynomial, that is constant polynomial.
Sorry. So v of h is what? Zero set?
The
We don't
notation
know.
is a little bit confusing because we are using this. I'm in the statement of identity theorem. H they are using, that is my constant polynomial.
Okay. So you are saying if those condition holds, then h has to be 0. Since h is non-zero, then there exists some ni's. There exist some.
There cannot exist NIs. There cannot exist such NIs such that it is.
But RIs are different there. So okay, let's try to write. So since h is not equal to 0, this implies from identity theorem
To use identity theorem, we need a function, other function.
Sorry, what?
To use identity theorem, we need one other function.
Which one? No.
Right?
No.
Say in the statement of identity theorem, we say F, G, and H, right? 3.
No. This is not G. No, not 3.
Oh, I'm sorry.
Identity theorem is just F with F and G.
Oh, I'm sorry. I'm confused. Sorry. Please continue.
No problem. Okay, so as we have cleared now that to prove, now we have to prove star. Okay, so star is a thing we need to prove. So if so induction hypothesis says, so we are to prove star, we are using induction. So induction hypothesis says that if h is not equal to 0, some polynomial, let's say new polynomial, we don't know, some okay, h or okay, ua, okay, some polynomial ua, so some polynomial u is not equal to 0 if polynomial u is not, okay, let's say h only. So just think h is not that only, because when we apply induction we are in general polynomial. If polynomial h is not equal to 0, then that polynomial h is not equal to 0 for a belongs to n1 cross up to and so on. And so now I'm writing m, where cardinality of ni is greater than ri for all m. Okay, and m is now, so assume this statement for m less than n. Okay, so from the induction hypothesis we can use this statement. If whenever h is non-zero, then we have the non-zero set dh. So basically dh is equal to all those points. There are points from n1 cross up to and so on nm, such that cardinality of ni is greater than ri for all m. Okay, so now if I take m to be n minus 1, as in my case here, so I have used now I know h, since a1 to an minus 1, when I take a1 to an minus 1, then this is non-zero. This implies h dash is non-zero. Then I can apply induction hypothesis and can say that h dash b1 to bn minus 1 is non-zero for all bi belongs to ni, some ni. Now I have produced these ni was not there earlier. Okay, from the induction hypothesis I have n1 to nn minus 1, and this is a finite set. Ni's are finite set, which are bigger than ri. Ri were fixed numbers coming from the polynomial f, which we have fixed already. Now okay,
so now only we need to extend the nr term, the last term, the last set.
Yeah, exactly, extend this large set. Now I will
the
use
last
this
one, or other is already formed. Okay,
yeah, so now I will use this part. Oh, okay, m already I have used, so don't confuse with this m. So degree of h is m. Okay, so this m maybe I will not say m. Okay, yeah, some k is already used, so q, I don't know, yeah, for all q, I less than q. Okay, anyway, so you have this. Now we will use this part, h of x1 to xn, this one. Sorry, yeah, so now we can use this part. Now what you do, you take this set n1 to, you have this set means you have the points from n1 cross up to and so on n minus 1. Okay, you take this set from this set, you take any point b1 to bn minus 1 from this set, and put it here. Okay, put it here. Then what will you get from this? You know that number of so h will be non-zero. Okay, h will be, okay, let me write this down. H of b1 to bn minus 1, comma, some xn, that now this is a polynomial in one variable. This will be non-zero for or maybe let me write this, equals to 0 for some finite set, because we know that degree is fixed, and that finite set has cardinality less than m. Okay, less than or equal to m. For some finite set it will be 0, because this is a one variable thing, and in one variable we know already. So h will be 0 for some finite set. Now and again this itself is non-zero, because b1 to bn minus 1 are coming from h dash, and from there we know that this point comma an is non-zero. So it's kind of non-zero thing appearing again and again. So for each point b1 to bn minus 1 we have some finite sets. So b1 to bn minus 1 xn is not equal to 0 for for a a means the full set, full integral domain a, but finitely many. So just on finitely many points it will be non-zero, and at other points it will be 0. Sorry, it will be 0 on just finitely many points, and it will be 0 on the whole ring, the left out points, not left out. Okay.
Now we can use the induction again, right? Because
No,
one
no,
variable
not
we
induction.
already
We don't need to use induction since this is a finite set. I'm saying for every point you can do that. So you take b1 to bn minus 1. Now you have to just produce
it is for one variable,
n.
right? Now it become to one variable where
it
h is non-zero.
So I'm not.
So
okay. Let me complete. So you have this part n1 to nn minus 1. I have to produce nn. Okay, which is big enough, right? So what I will do, for every point I will find some set of xn. Okay, some set which is infinite. Infinite means it is dense means it is all but some finitely many points, and it will happen for every point of this set, for every point of n1 cross up to and so on nn minus 1. Okay, this belongs to this set. Okay, for all the points you do the same thing. Now these are a finite, so this set is finite, so you are doing this for finitely many, this is finite. So you are finding xn for finitely many set, for finitely many set. And what my claim is, the intersection will be a infinite set. That's what I'm saying. So okay, so corresponding to this we have h of b1 to bn minus 1 xn not equal to 0 for, let's say, a minus now I have to use some notation. Let's say, okay, c1 to cs. Okay, some finite set. Now from other point you will get a minus, it is non-zero from other point. So you take b1 dash bn minus 1 dash. Just I'm doing for 2 points right now. If I take this from this set again, I will get some finite set, let's say d1 to ds. Now I know that h is non-zero at this comma this set, and this comma okay, so b1 to bn minus 1 comma yeah, so at these points, and these are coming from ni's, and b1 dash bn minus 1 dash. Okay, now I can write, I think, bn, where bn belongs to a minus c1 to cs, and from this bn where B n dash belongs to A minus d1 to ds. Okay, so these two things we have. Okay, now what you do, now you know that h is non-zero at these points, exactly at these points h is non-zero. H is non-zero at these points. Now you need to, so these ni's you already have. Now what you can do, you can just intersect these two sets, intersection. When you intersect these, then you will get some infinite set. Okay, and you can do this for all the set n1 cross nn minus 1. This is a finite set, you do it for a finite set. So what you are doing, you are intersecting infinite sets finite times, and these are special, that these are the complement of this set is a finite set, then you will get some infinite set. That's what I'm saying. You can try this. So you will get infinite set from here. Okay, and you just take some finite set which is bigger than, from this set you take some n which has cardinality bigger than Rn. So this is the idea. Is that clear? You can try this out, and I think you'll get a clear picture. So the idea is, this is finite. You cannot say if this is infinite. The set is infinite.
Which set is not infinite?
So this set is finite. So this process, what you are doing, you are getting some, for xn you are getting some infinite set. It is that is special, that complement.
Yes, fixing n minus 1 points, we are getting one infinite set.
Yeah.
Now varying all those combinations,
Right.
still we are getting, every time we are finding infinite sets. Now we want to take the intersection because we
Right.
want a large enough set. So, and that should be an infinite set.
That should be an infinite set, because these infinite sets are special, that complement is finite. So it's not like you will get 1 3 5 7 and from other set you will get 2 4 6 8. This thing cannot appear, because complement is infinite. Sorry, complement is finite. So that's why you will get some infinite sets. You will get
So
the
now
intersection.
what I want to ask, ma'am, is if I directly use that hypothesis to n equal to 1, fixing n minus 1, because now the resultant polynomial will become in one variable, right?
Right.
Take any, fix any point in ni, and the resultant polynomial will become one variable. Now induction hypothesis says there exists an ni. Okay, you use that thing only, but for every element, for all those combination, you use the hypothesis.
Yeah, because
and
we have
for
to.
every time you add a infinite set, and then you take intersection.
Exactly. Yeah. Exactly.
Okay.
Yeah. So from there you get an infinite set, and you can just pick some finite set from there, which has cardinality greater than Rn, and we are done. So if and now so what we have done, we have produced. So we have produced ni's such that, so that a star holds, and a star hold, then by identity theorem f has to be the zero polynomial. Okay, great. Okay,
That was a good proof.
yeah. Yeah, these questions are intriguing. So yeah. Okay, so maybe for 2.3 I can give you an idea if you want. So I think I'm done with the time. So okay. So basically it says if you have phi from ax to AA, and f goes to all those polynomials, let's say sigma. So this is a set of all the functions. Sigma functions. What's that? Functions from A to A. So this is the set of functions. So it says f goes to sigma where and sigma is a function from a to a such that a goes to fa. So this is the function. This is the function phi, which sends every polynomial to a function from a to a. Now you have to prove that this map is phi is surjective if and only if A is a finite set. Sorry, not finite set. This is a field. It has to be a field. Okay. So, for example, what you can do, you can try to prove that if A is a finite field, okay, so I can just write this side. If A is a finite field, then you need to prove that if you consider a function, then it can be represented by a polynomial. That's what it says.
These are like any functions or field homomorphisms or ring homomorphisms?
No, any function. There is no restriction, so to say, at least, yeah. So f a to a goes to f of a. Yeah, this is just a function. Function means a point cannot have two images, and every element of domain should map to somewhere. Okay, so just a function. Now, so if A is a finite field, A is finite, field is important, then what we can do, you just take sigma to be what? Now we don't know about f, we just know about sigma. There's a function. So what I can do, okay, I can just remove this. So yeah, A is finite field, and sigma from A to A, let's say AI maps to BI. I will number this set to be like A1 to AN. Okay, just because this is a finite field, this has finitely many elements. I've written it down.
These are evaluation maps, right? Evaluation maps.
Yeah, these are evaluation maps. So we are saying
these are ring homomorphisms, right? A to A.
But you don't know evaluation. So from A to
any
F,
polynomial we are taking and we are evaluating at any point. That is what the function.
This will be a homomorphism, but function you cannot say. If this is a function, you cannot say 0 will map to 0 or something like that, or maybe like f of a plus f of some g of a. So firstly, the point is, these are just the function. Any element can map to any element. There's no restriction as such. So you take sigma. I'm saying.
Okay, understood. Yeah. If I take constant functions, then means.
Yeah.
It doesn't.
So yeah, exactly. Okay. So you take sigma, where any element of AI will map to some element of BI. So I am just naming it to be BI. Now I have to produce a function here. Produce a polynomial. So we are saying all the functions are polynomial functions that we want to prove for if A is finite field. So you take sigma, which I can write AI maps to BI. Okay. Now what we can do, let fx is equal to f. I don't know. I'm just writing a general notation. C okay, n I have used, so let's say m x raised to power m. Okay, some new some f this is. If I can find the coefficients such that if so what we want f of ci's belongs to a ci belongs to a such that f of ai is equal to bi. Okay, let's write cj for all j from 0 to m, such that f of ai is equal to 0 is equal to bi for all 1 to n. So the elements are 1 to n, and like this is this these bi's also these bi's also belong to a. So this is from map from a to a. So what we are saying, if we can find out the coefficients such that f of ai is equal to bi, then we are done, right? We really need to find this m ci's, okay, c0 to cm. So let's try to write the equation. If that equations, if those equation can be solved, then we are done. So let me write. So I'm saying f of ai is equal to bi. So that means c0 plus c1 a1 up to and so on cm a raised to a1 raised to power m is equal to b1. Second equation, you take a2, then it should so we are saying f of ai, f of a1 which is equal to this, f of a2 which is equal to this, a2 raised to power m should be equal to b2. Okay, this we want to find the coefficients and m such that this will happen. Up to and so on, f of an is equal to c0 up c1 an up to and so on cm an raised to power m is equal to bm. Okay, so sorry, not bm, this is n. Okay, so we are not saying bi's are different, we at least know ai's are different, ai's are distinct, because these are elements of a. Okay, we have noted it down to be a1 to an, so these are distinct. But b1 b2 we don't know, it could map anywhere, it could map to the same element, it could map to just a1, all the elements could map to a1, so all the bi's could be equal to a1. Okay, so these are just system of equations. What I can write it to be like this, a1 a1 a1. So the coefficients are variables that you need to figure out, right? If I can figure out the coefficients, then I can say this f is equal to sigma. So a1 square, so this will multiplied by this will give the first equation. So you have a1 raised to power m. Okay, I can write one more line, 1 a2 square a2 raised to power m 1 an square up to and so on an raised to power m. This should be equal to b1 up to and so on bn. This should be equal to this that we want. We want to find CIs such that this happens. Now, okay, if so, we want to construct such a f. So I can pick m according to my knowledge. So I can take m to be equal to n minus 1. Why I have taken m to be n minus 1? Then what will happen? This will be a n cross n matrix, right? Because you have m plus 1 columns, and there are n rows and m plus 1 columns. So if m is equal to n minus 1, if I pick this, then this matrix, so let's call this matrix to be A. Then okay, A is a notation already, so let's say this matrix is B. Then matrix B is a square matrix and its determinant, can you tell me what will be the determinant if you know this matrix? Does this matrix look familiar, or at least you know the determinant, how a determinant will look like?
Product of ai minus aj.
Yeah, exactly.
Product of all.
Where I is greater than aj. So yeah, this will exactly. This is a Vandermonde matrix. So this has this determinant, well-known matrix. Now, if this is the case, and you know that AIs are not equal, so AI is not equal to AJ for all IJ, I not equal to J. If I is not equal to J, then these are not same. So this has to be non-zero, right? So this product will be non-zero. Since determinant is non-zero, we can invert this matrix and we can get the CIs. So this is just bunch of linear equations, and we know when it will have a solution and when it will not. So if the matrix has non-zero determinant, then you can invert it and you can get the get CIs, C0, C1 up to and so on Cm. So you will get this. Is that okay? So in finite field, so at least in finite field we know if element inverts, then also we know that inverse exists. Every element has inverse, so there is no issue with the inverse thing and anything. In finite field, this implies we can find CIs uniquely, and that will serve the purpose, right? So for finite field we are done. Is that clear?
Can you explain the last part?
Okay. So
Means if determinant is non-zero, that is clear now.
So determinant is
I was
non-zero,
not-
so you can invert it. So it's like you have system this system. So from linear algebra we have done that bx is so I've written it to be bx, so that's why I've written b, and you have some c this. So if you have this system and you have this m cross m and n cross n, n cross n, n cross 1, and you have n cross 1, then this system has a solution, has even unique solution if b is invertible. I've used this fact. So basically the equations are linearly independent, so bi will not play much role. So you will get C as to be uniquely determined. So you have m equations, m variables. M plus 1 variables. So m plus 1 is same as n is equal to m plus 1. So n is equal to m plus 1. So you have n variables and n equations. So you can solve it because b is invertible. I've used this fact. So the CIs were indeterminate, like those were the variables we need to figure out. So when you invert B, you will get some values for CIs, and that will give you F. And when you have F, and F was something such that F of AI is equal to BI. So what you have done, you have considered any arbitrary sigma, some function sigma from A to A, and you have proved that this sigma of AI is same as f of AI for all AI, because I have assumed that f of AI is equal to BI, and I have produced this coefficients. I have figured out what will be the coefficient, and so we have the polynomial f. Is that clear?
Yes.
Okay. So so this is the case. Okay, try to prove the other side, and we can continue next time if you have any doubt in that, or at least I'll try to write it itself in the notes, the solution of 2.3. Is that okay? Try.
Okay.
So for the other side, for the other side, what you can do, just for the other side, you can try to prove that if A is an infinite field, then also you cannot do that. Okay, that you can actually easily prove. That also it cannot be possible. You cannot prove that this is surjectivity. You cannot prove that this is surjective. At least produce some function such that you cannot find a pre-image, or you cannot find a polynomial to write that function. And when A is a non-integral domain, or not even integral domain, this is not a field, maybe just a commutative ring, not a field. So you can try to prove in two phases, like if A is an infinite field, then it is not surjective, and if A is a commutative ring which is not a field, then again this is not surjective. So just try to prove that. I will anyway write in the notes the solution. Yeah, I'm done for today. Yeah. Any doubts?
No, ma'am. Thank you.
Okay, great. Thank you.
Ma'am,
Yes.
ma'am, the statement is true for finite field.
Can you speak louder a little bit? I cannot hear.
The theorem is true for finite field, only the finite field.
Yeah. So statement is true for only finite fields. So if you have surjectivity, then it is a finite field. So you can prove the contrapositive statement that if a is other than like finite field, then it is not surjective. So other side I was proving like that. Yeah, but the statement says if it is surjective, then if and only if a is a finite field. Yeah.
And the DIs we are considering in the system, they are all distinct.
Can you speak little bit louder because
In the system of equation, the DI we are considering all are distinct.
yeah, AIs are distinct, right?
DI.
No, BIs are not distinct. I don't know what BI is like. Maybe what can happen, all the AIs will map to 0. Then all the BIs will be just 0. BIs are just representations for like where AI maps. So it could happen that AI will map to. Subjectivity is not of sigma. It's the subjectivity of sigma is not something we are proving. We are proving that all the functions from a to a can be written as some polynomial like of this kind. So surjectivity means if you consider any sigma from right hand side, like any function from a to a, then you can find the polynomial f such that sigma of a is equal to f of a for all a belongs to a. So that you are proving. Any function can be will be a polynomial function. Polynomial function means sigma of a is equal to fa for all a belongs to a, where f is a polynomial.
Oh, okay. Basically, we
And
want to
these,
find
yeah, sorry, yeah.
uh, uh, we we need to find the polynomial and the
Yeah, we
coefficients
need to
are
find the polynomial. BIs has no role in this. BIs could be anything. Role in this is like you can actually, for example, for infinite field, you can try to find some sigma from a to a, such that where a maps somewhere. Then you can try to find. For example, I will just write if so 0. So a is a commutative ring which has 0 and 1 at least. Okay, so what you can try to find, 0 maps to 0, let's say 0, okay, let's say 1 maps to 0 and all the other elements, okay, 1 maps to 1 and all the other elements will map to 0. Let's say you consider sigma to be this, 1 will map to 1 and all the other elements a from a minus 1, like you just take the set a minus 1, all the other elements of a will map to 0. So you get, so basically this function cannot be represented as a polynomial function if a is an infinite field. So I'm saying if a is an infinite field, then you cannot find a polynomial f such that this happens, and you can use this. Okay, I can answer this at least for infinite field. So what I'm saying, if there has to exist a polynomial, right? Then f of a has to be 0 for all a belongs to a minus 1, right? Because f of a should be same as sigma of a, right? If there is a polynomial such that sigma of a is equal to f of a for all a belongs to a, then what should happen? F of a has to be 0 for all a belongs to a minus 1. Is that clear?
yes, ma'am.
Now Now you know that A is infinite field, and you have just seen the identity theorem. Then f of A is equal to 0 for infinitely many elements, then f has to be the zero polynomial. Now you can use with the theorem that f could have any finitely many roots, because you are just in one variable, like one x, ax you are talking about. F belongs to what? Where? F belongs to Ax. You have just one variable and you have infinitely many roots of F, right? This is not possible. So you have constructed a function from right hand side, from the codomain, which does not have any pre-image. Pre-image should be what? Some polynomial such that sigma of A is equal to f of A for all A. Is that help? Is that help?
Yes, ma'am.
Okay, great. Any other question? So just try to prove for commutative ring, which is not a field now. So I prove for infinite also, infinite field, but which is not a field, and commutative ring, then you can try. Again, this will not be surjective, so you have to produce some sigma such that it does not have any pre-image. Okay, yeah. Anything else?
No, ma'am.
Okay.
Thank you.
Thank you.
Thank you.
Yeah.
Yeah, enjoyed it.
Okay, great. Good to hear that.